the ground shake.
Welcome everyone to a new video. Today we'll be actually coding Dijkstra's algorithm. If you didn't see the previous video, I was actually explaining the algorithm, and we ran the algorithm together against a weighted directed graph of 8 nodes using an 8x8 matrix. We filled it, and I guess it was a bit clear. If you didn't really understand it, you'll understand it in this video. If you didn't understand it at all, please rewatch the video, or actually play with this animation I got from Carleton's University. It's a lovely animation. I'd actually play it right now to give you a brief idea of what's going on. The way this animation works is if you have visited a node, it will be green. If a node is unsolved, it will be blue. If it's solved, it will be red. For example, here we visited the source node, which is O, so we can get to the source which we are already on using 0 points. Of course, that's free since you are already there. You can travel to A using 2 points, you can travel to B using 5 points, you can travel to C using 4 points. So we would pick the shortest or the cheapest of the three to get to, which is 2, and we would actually travel across this cheap lovely path, and we would pay the 2 points and visit A, and we would run the same algorithm from A. We can get to F using 12 points, 12 more points, because remember we already paid 2 to get to A. We would pay another 12 to get to F, so that would be a total of 14. Same goes with the 7 plus 2, 9, 2 plus 2, that's a 4, and remember 0 plus 5, that's a 5 to B, 0 plus 4, that's a 4 to C, since we can also visit them from the source node. So we are running the algorithm against all the green nodes. However, there's an interesting case right here. When both of these have a tie, we can get to both using 4 points. So we'll choose one randomly. The animation chooses B and goes on from there. It visits F, D, E, and C, since these are the nodes you can get to from the visited nodes O, A, and B. After that, we would get the cheapest, which is 4, which is on C. See here, we have actually two paths to get to C. We can pay 5 using a path from B, and then from actually O, A, B, and C, or we can just go from O to C using 4 points. So this is the cheaper path. We would just disregard this. We would focus at this path. This is the path we would actually take if we ever wanted to visit C, and we would love to visit C right now to discover the neighboring nodes to C and discover new paths. Hopefully the new paths would be better than the already discovered. However, this is not the case, and we would keep just running the same algorithm against all the other nodes and visiting all of them. If you didn't really grasp the concept, there are some subtitles that you can read. I think actually the animation is pretty good, and if it's still unclear, please pause the video, visit the link in the description that will take you to this animation of Carleton's University, and have a look at it, try to understand it. If not, please rewatch the video. If not, please just bear with me. I'll try to explain it while we are coding it. So today, as I said, I'll be using Java. I'll use a text editor. In this case, it's Sublime Text. I would like you to see the previous like 20 or 30 lines, so you can follow the flow of the algorithm and the code. I'm using the scanner because right now I'll have a static scanner object called scan. This is like scanf or in C, or Cn and C++ and so on. That's the standard input, which you can get from the command prompt or terminal or something. This is how you interact with the user. Okay, so now let's declare the stuff with the matrix. Matrix new int 8. Since we got 8 nodes, I would be using an 8 by 8 matrix. I would also have a distance array. Let me copy this. I would have a visited array. I would have a path array or a predetermined path array. And I would have, oh yeah, I would also have scanner is equal to new scanner system in. So that's my scanner input, and that's not a declaration. I don't know why did I forget that. And my minimum is supposed to be infinity, but 999 would do compared to the values we're having here. So what else I need? Next node. To hold the next node I'm going to visit number. Pretty much I will represent the A, B, C, and so on as 0, 1, 2, 3 respectively. So I'll start with 0 to 7 as A to H, and this is how it represented in the program to make life easier. As I said, that would be the visited array, that would be the predetermined path array, which is, for example, where I store the node I just came from to this node, which is in this case, for example, A, and the distance would hold the 85. I would then go ahead and grab the input from the user, so that's the easy part, only if I can type it. So matrix I and j is equal to scan dot next int. If that thing is equal to 0, that thing should be equal to 999, which is my infinity. Since there is no path to get to that, it is infinity in the program. And I'll just use this lovely loop to initialize everything to 0 in the predetermined and visited arrays, and that'll be all for the inputs. Now let's actually run Dijkstra's algorithm. Let me put a lot of new lines to separate the lovely algorithm from the input and the output phases. I just spotted a mistake right there, typo. And okay, let's basically visit it. 0 is equal 1. Let's visit the first, very first node. Let's grab the distance from the first row, and that would do. Actually, nope, we just get the whole thing. And of course we need to make sure distance 0 is equal to 0. That's just a sanity check. And now let's run the loop. That would go over all nodes, and then we'll have another loop. Which will update distances